Welcome back to The Explainer. Today, we're stepping into what is basically a historical detective story. We're looking at a massive clash of paradigms involving one of the greatest scientific minds in history, and it's all centered right around the foundational mysteries of quantum mechanics. This was a literal battle of ideas that completely flipped our understanding of the universe.
Okay, let's dive into this. Was Albert Einstein, the man literally synonymous with genius, fundamentally wrong about the nature of reality? I mean, it's a stark question, right? But to understand why we're even asking it, we have to travel back to a time when physics was going through this incredibly uncomfortable revolution. We need to look at exactly what Einstein was fighting against.
And this comparison perfectly captures the philosophical war at the heart of our story. On one side, we've got classical physics. This is the universe just the way Einstein loved it. Predictable, a place where objects have definite, concrete properties whether you're looking at them or not. And crucially, interactions are local, meaning nothing travels faster than the speed of light. But on the other side, we have the newcomer, quantum mechanics. This radical new theory suggested the universe is inherently probabilistic. It was saying that the properties of particles are literally uncertain until the exact moment they're measured. Plus, it hinted at these incredibly strange, non-local possibilities. Einstein just could not accept this probabilistic universe. As he famously put it, God does not play dice.
Section 1. The Quantum Reality Problem. Heisenberg's Uncertainty Principle. To really grasp the core of Einstein's frustration here, we have to look at Werner Heisenberg. Quantum mechanics dictated that we absolutely cannot know both the exact position and the exact momentum of a particle at the same time. The more precisely you measure one, well, the less you know about the other. And Einstein deeply distrusted this. He felt this wasn't some profound truth about nature, but rather a flaw in the theory itself. So, in 1935, Einstein teamed up with two brilliant postdoctoral researchers, Boris Podolsky and Nathan Rosen, and together they published what we now call the EPR paper. Now, their goal wasn't to say quantum mechanics was outright wrong. The math honestly worked way too well for that, but rather to prove it was incomplete. They wanted to show the theory was missing something fundamental about reality.
To build this attack, they needed a rock-solid foundation, so they defined an element of physical reality. They stated, if, without in any way disturbing a system, you can predict with absolute certainty the value of a physical quantity, then that quantity must be a real, pre-existing element of reality. In plain English, if I can know a particle's momentum without even touching it, that momentum must have existed before I knew about it. It couldn't have just popped into existence out of some probabilistic fuzziness.
Section 2. The EPR Thought Experiment. Enter Alice and Bob.
Armed with that strict definition of reality, EPR designed a completely brilliant thought experiment to back quantum mechanics into a corner. Let's move to the crime scene of our mystery, using the classic Alice and Bob analogy, the two most exhausted hypothetical people in all of physics. It just keeps things clear and avoids a bunch of dense math. So let's walk through this clean 1, 2, 3 sequence. Step 1, two particles, particle A and particle B, briefly interact and then fly apart. Step 2, they separate by a vast distance. We're talking light years apart. Step 3, because of that initial interaction, their properties are deeply correlated due to conservation laws. So if Alice measures particle A, she instantly knows something about Bob's particle B.
And right here, this is the core conflict. This is exactly why EPR challenged quantum mechanics so fiercely. You see, Alice has a choice. If she measures the position of her particle, she instantly knows the position of Bob's particle. But actually, scratch that. If she chooses to measure momentum instead, she instantly knows Bob's particle's momentum. Now think back to that EPR reality criterion. Alice hasn't touched Bob's particle, it is light years away. Yet she can predict its position or its momentum with absolute certainty. EPR argued that since Alice can choose what to measure without ever disturbing Bob's side, Bob's particle must have possessed both a definite position and a definite momentum all along. But quantum mechanics says a particle can't have both simultaneously. So EPR concluded quantum mechanics has to be incomplete. It's missing these pre-existing hidden variables.
The only alternative explanation, the one quantum mechanics seemed to be implying, was that Alice's measurement on her particle instantaneously forced Bob's particle to take on a definite state, regardless of the vast distance between them. And Einstein absolutely despised this idea. He famously mocked it as spooky action at a distance. To him, this violated the ultimate speed limit of the universe, established by his own theory of relativity.
So the crucial point is this exact bedrock assumption that Einstein flat out refused to let go of: local realism. Realism means objects have definite properties before we even look at them. Locality means no physical influence or information can travel faster than the speed of light. Einstein firmly believed the universe had to operate on local realism, but quantum mechanics seemed to say otherwise. And for decades, this was just a philosophical debate, a stalemate between physics giants.
Section 3. Bell tests local realism, the 1964 breakthrough.
Then, in 1964, an Irish physicist named John Bell proved that this philosophical debate wasn't just philosophy anymore. It could actually be tested mathematically. And this brilliantly illustrates how science progresses. Bell derived an inequality, a mathematical limit. He showed that if Einstein was right and the universe operated on local realism with these hidden pre-existing variables, then the statistical correlations between measurements of entangled particles could never exceed a very strict limit. But if quantum mechanics was right and the universe really did feature this spooky action, those correlations would break that limit. Bell essentially drew a line in the sand.
Just look at how long this paradox haunted the scientific community. The EPR challenge was laid down in 1935. It took almost 30 years for John Bell to publish his theorem in 1964, giving us a way to test it. And then it took almost another 20 years before the technology actually caught up to the math. It wasn't until 1982 that French physicist Alain Aspect finally performed the defining experiment.
Section 4. The twist. Violating the inequality.
Right, so in 1982, Alain Aspect and his team put Bell's inequality to a rigorous, real-world test using the polarization of paired entangled light particles, photons. They measured the correlations between the particles at incredible speeds to ensure literally no light speed signal could secretly pass between them. And the number of local hidden variable theories that survived Aspect's rigorous test? 0. Absolutely 0. Bell's mathematical limit was violated. The correlations they measured matched the wildly strange predictions of quantum mechanics perfectly and completely shattered the limit set by Einstein's beloved local realism.
Now, what's really interesting about that 0 is the profound implication. Einstein was wrong about this fundamental aspect of reality. The physical universe does not have a unique, classical reality independent of observation. The universe is fundamentally non-local. That spooky action at a distance, it's not a math error. It is a fundamental built-in feature of our universe. What Erwin Schrödinger originally termed Verschränkung or entanglement is an absolute, verified reality. Particles can be so deeply linked that the state of one instantaneously defines the state of the other, no matter the distance.
Section 5. The era of entanglement, from paradox to power.
Einstein, Podolsky, and Rosen tried to expose a fatal flaw in quantum mechanics. But instead, they accidentally put a massive spotlight on the theory's most powerful feature. Because entanglement is real, we are literally building our future technologies based entirely on it. Quantum cryptography uses entanglement to create theoretically unbreakable codes. Quantum teleportation allows us to transfer the exact quantum state of a particle across vast distances. And quantum computing leverages these entangled states to perform calculations at speeds that would take classical computers millions of years. Einstein's perceived flaw has become the very foundation of tomorrow's tech.
It really makes you wonder, doesn't it? If the greatest challenge to quantum mechanics actually birthed an entirely new era of quantum technology, what other seemingly incomplete or paradoxical theories that we're debating today might be hiding the unimaginable technologies of tomorrow? Well, I hope this explainer helped demystify the EPR paradox for you. Thank you so much for exploring this with me. Keep questioning, keep learning, and I'll catch you in the next explainer.